talking about linear velocity and angular velocity. This is going to feel kind of like a stretch from what we've been doing these past few days, but I promise it's not too bad. Where did I want to go with this? Okay. Velocity means speed, all right? And for those of you who are taking physics, this is probably actually going to be pretty helpful in your physics class to learn this stuff. So 2 for 1, Mr. Bain can thank me later. So velocity means speed. Okay. So how I'm going to introduce this to you is we're going to look at an example, a theoretical example. And what's nice about this is that we're actually going to start applying what we learned to the real life world, which is kind of cool. Because we like finally, right? We like learning math so that we can actually apply it. All right, so let's imagine, right, here's a big circle, it's a big circle. Okay, we've been using circles, so that should feel familiar. It's going to be a radius of 2 miles, and I'm using miles for a reason you'll see. Now imagine that this big circle is a circular racetrack, okay? And we have a little car right here. You see these little wheels. It's a pretty old car, okay? And this car is going to be going 5 miles per hour around this racetrack. 5 miles, because it's an old car. It's going pretty slow. It's going 5 miles per hour.
It's an old car.
So, we can actually use this idea right here to help us realize what the formula for finding speed is. All right, our speed we know is 5 miles per hour. Our speed, girl, do you know how to spell? This is why I teach math and not our speed.
Seed.
Our speed is 5 miles per 1 hour. So speed, or our velocity, right, because velocity means speed, our velocity equals the distance we travel divided by the time we travel for. All right, so this is something that you're going to use in physics. Again, Mr. Bain can thank me later. V equals D over T. Now, what I want to point out here, and this is really, really important. All right, let's say we went this distance, all right? Let's bring it back to angles. Let's bring it back to trig. What's this distance right here? This isn't a straight line. This is a curved line. This is our arc length. And so now, oh, we learned arc length earlier this week, so maybe like, whoa, we're actually using it. I know, cool. So we know that our arc length formula is R, or S is arc length, right? Equals R theta. Our radius times our theta. All right? So instead of using D, we're not going to use D. You can save that for physics. In trig, we're going to use S as our distance. Okay. So that means our linear velocity, this is linear velocity, equals our arc length over time. So if you're going to write a formula down, this one right here. Okay? Linear velocity equals the arc length divided by the time. All right. Again, this is the formula you want to be writing down. You want to remember it. Okay? I'm going to rewrite it. I'm going to rewrite these 2 formulas up here really quick. Theta, and then V equals S over T. All right, and we're going to do a really quick example just with this formula so we see what's going on here, right? So, if our speed, let me rewrite it right here, equals S over T. If our speed is 5 miles per hour, so 5 mph, if I ask you, like, how far did this car move in 3 hours, this is what you would do. right? So your linear speed equals your arc length divided by your time, right? So the arc length is the distance, so we're still trying to find that. We're trying to find the distance, and then we're doing after 3 hours. 3 hours. So another way we can write miles per hour is 5 miles per 1 hour equals S over 3 hours, right? We're gonna multiply both sides by 3 hours. The units matter a lot, all right? So like miles, hours, that matters a lot, like a ton when you're doing a velocity. When you're doing physics, keep that in mind. That's why like Mr. Bain was having you convert a bunch of stuff. The units matter a lot, and especially matters in this case. So make sure to label all of your values with your units when you're doing this, all right? So we got over here, we multiplied this side by 3, we're gonna multiply this side by 3. All right, and then we're gonna get S equals, the hours are gonna cross out, right? S equals 3 times 5, so that's 15 miles. So that means this little car right here, after 3 hours, it's gonna travel 15 miles around the circle, okay? So that is how we would use that formula. Now, this is just one type. Linear velocity is just one type of velocity. There's another type of velocity. It's this right here. How fast is it spinning? How fast is the angle changing? All right? So, the formula for that is going to be this right here. Bear with me. Omega equals theta over time.
You should label them.
Oh, I will. So this right here, this is not a W. This is omega. Omega, all right? This is our angular velocity, so how fast our angle is spinning, how fast our angle is changing. Angular velocity. Over. All right. Our angle in radians, right? Our angle, our theta, our angle in radians divided by our time. Write this formula down. Omega, or our angular velocity, equals theta over time. Our angle over time. All right? So that means our speed, our angular speed, is just how many angles we turn or we change over time. The same way you do miles per hour, you're doing radians per time. Yeah? You're doing the angle per time. Okay? So, how do we then relate angular velocity to linear velocity? All right? This is how. Right? This is how. So, remember up here that our linear velocity is v equals s, our arc length, over time. Well, s, we know, is equal to the radius times theta. So we can just replace this right here. R theta divided by time. That looks kind of familiar, right? This right here is this right here. So that means that our linear velocity is equal to the radius times our omega times our angular velocity. Okay? So V equals R omega. All right? Let me write that out in words. Our linear velocity equals our radius times our angular velocity. Write that down, okay? So, all right, so let's find the angular velocity, and then we're gonna connect the linear velocity to the angular velocity. So I'm gonna give you an example, right? So let's say, right, angular velocity is theta over time. So let's say that the angular velocity for this example, the car is going all right, so we can actually use our linear velocity to find theta, to find our angular velocity. So let's start with the example we were doing earlier, right, where we had a car going 5 miles per hour around a circle that has a radius of 2 miles, all right? So we know that v, right, our velocity equals our arc length, s, over time. It's right here. Our arc length is the same thing as the radius times theta, all right, over time. Yeah, this equals this. Cool. That's how we discovered that, right? So, if we have 5 miles per hour, that means our speed is 5 miles per 1 hour, right? So if we want to find theta, we would just plug in 2, right? 2 miles times theta divided by, right now we're looking at 1 hour, so we'll keep it at 1 hour. That's our time, 1 hour. All right? So now we're going to multiply both sides by 1/2 to get rid of our, to get theta by itself. That's the word I'm looking for, to get theta by itself, right? So then theta, right? All this stuff would cross out, right? And then we would just be left with 5 over 2. Okay, so theta equals 5 over 2 radians, or 2.5 rad. So that means after an hour, right, 1 hour traveling, after an hour, this angle has gone to about 2.5 rad, somewhere over here. Right, so after an hour, the angle has moved this far. After an hour, it's moving very slowly, okay? And the way that we would find the angular velocity then, right? Angular velocity equals theta, 2.5 rad, over time, 1 hour. So that means our angular velocity for this right here, this car that's traveling 5 miles per hour, its angular velocity is 2.5 rad per hour.
Rad.
That's so, oh, that's a good joke. Okay. That's enough of this example. That's enough of that. There is one other thing that I want to look at, because we're not always going to be using miles per hour. We're not always going to be using a little car, okay?
Bye, car.
Bye, car.
It was totaled.
Okay. We're going to be using sometimes these things called revolutions. What's a revolution? Not the French Revolution, not the, you know.
To the revolution. Deshaun will get that joke.
Oh, is that Hamilton?
Yeah.
All right. One revolution is just one full circle. And hopefully at this point we know a full revolution is 360 degrees, but it is also 2 pi radians, right? Half a revolution is pi radians. A full revolution is 2 pi radians. So we're gonna be doing like a lot of converting and stuff. So just keep that in mind, all right? So let's try an example, okay? Awesome. All right, so let's say that we're given that something is moving in a circular fashion, right, at a constant rate of 60 RPM, right? That means revolutions per minute. So it's moving 60, so for every 1 minute, it's moving around the circle 60 times. That's pretty fast, right? I want to know how many radians is that per second, all right? This is how we would do it. This is how we would convert it, okay? We would take 60 revs, or revolutions, per 1 minute, right? And then we ask ourselves, how many radians are there per 1 revolution? Well, we just said, right? There's 2 pi radians per 1 revolution. But we're not there yet, right? Because right now we're in minutes and we want to be in seconds. So then ask ourselves, right? How many seconds, or no, how many seconds are there in a minute? All right? So for every minute, 1 minute, how many seconds are there? 60. I know you might be asking yourself, well, I know why is 60 seconds at the bottom? Because we have minutes down here in the denominator, so we want to get minutes in the numerator so that they cancel out. Yeah? Okay. So once we do this, right, the revolutions cancel out, the minutes cancel out, and the only units we're left with are radians over seconds. So our answer is going to be radians over seconds. Radians per second, which is what we wanted, right? So now let's look at the numbers that are left. We have 60 times 2 pi times 1. So that's 120. 120 pi over 1 times 1 times 60, which is just 60. All right? So we get 120 over 60 pi radians per second. We can reduce this down, right? 120 divided by 60 is 2. 2 pi rad per second. That came out to a pretty cool number. It didn't occur to me that 60 was going to end up doing that, but it should have. So there you go. 60 RPM is 2 pi radians per second.
Pause it.
Yeah. Did you start it? Okay. I'm ready. All right. So let's say that we're given that something is moving in a circle at 80 RPM. So revolutions per minute. At 80 revolutions per minute. And that this circle has a radius of 3 inches. All right? So radius is 3 inches. I wrote it backwards. I'm sorry. Whatever. Okay. So first, let's say they ask us, how many radians per second is that? So we're going to do exactly what we just did, right? 80 revs per 1 minute, right? Times, right, 2 pi radians per 1 rev. And then again, we're going to go from minutes to seconds. So we got 1 minute for every 60 seconds. Okay? And then again, we're going to cross out these units, and then we're going to get 160 pi over 60 radians per second. All right, so there's that. Then I want to know what's linear velocity. And now this is where we're going to put the radius in, right? So V equals R omega. So our linear velocity equals our radius 3 times our omega, which is our radians per seconds right now. Rad per second. All right. That is going to reduce to some fraction that I can't think of at the top of my head. Pause.
Okay.
If you do the math for that, you just reduce the fraction, right? This is going to leave you with 8 pi. 8 pi, and it's going to be in inches, right? Because this is in inches. Inches per second. Inches per second. And that's our linear velocity. So that object is moving around in a circle, right? At 8 pi inches per second. So that means after 1 second, all right, if we attached a string to the end of that object and it went around, all right, if we took that string after a second to find out how long that string was, that string would be 8 pi inches long. Okay? Okay. It's been a long day, guys. I don't even know. I was so confident in what I was saying, and then we started recording, and like everything just went out my head. But If you have any questions, let me know. The degrees, or the radians, or the angle, we're changing the angle that we're rotating at. So instead of measuring the distance on the outside, what would be the speed that we're moving in? I hope you can hear that in the video. Some people are racing. They're practicing their velocity. They're learning their velocity.
A knee slapper.
That's so funny. Okay.